Hi, hello, thank you very much. So I'm Avner Rothschild from the Technion, Israel Institute of Technology, and I'm honored to chair this session. I apologize for not joining you in Germany, but you know, the dire situation here in Israel make it simply impossible. My daughter is fighting the Hamas terrorists in Gaza, and I'm terribly worried for her. Yesterday, we were in a funeral of one of her classmates who died in a combat, and today in another one. We host in our home war refugees from the war zone in the north of Israel, a terrified single mother and her disabled daughter. And we expect missile attack from Hezbollah in Lebanon any moments. But let me assure you that Israel will prevail, and in the end, we will come out united and stronger from Saturday massacre in our people. In the plenary session this morning, we heard about the role of green hydrogen and other electrofuels such as ammonia and methanol in net zero. Unfortunately, the technologies for replacing fossil fuels by these renewable fuels from production to utilizations are currently lacking, certainly at the scale that we need them.
Recording in progress.
And this session discussed the scientific challenges we face on the way to the development and scale up of these technologies. We have 5 distinguished speakers from Germany, the United States, and Israel. Professor Peidong of UC Berkeley will open the session by presenting the challenges and progress in artificial photosynthesis, followed by Professor Banin of the Hebrew University of Jerusalem, who will present recent advances in photocatalytic semiconductor metal nanocatalysts for solar fuel production. Professor Beatriz from the Fritz Haber Institute of the Max Planck Society in Berlin will speak about the dynamic behavior of surfaces and interfaces during electrocatalytic processes in energy conversion applications. And Professor Valerie Karplus of Carnegie Mellon University will speak about the challenges of using hydrogen to decarbonize iron and steel production. And finally, we have a last-minute update, and Professor Christopher Hebling from the Fraunhofer Institute for Solar Energy Systems will speak about hydrogen production. In the end of the session, we should have some time for question and discussion with our speakers. So we start with Professor Peidong, who is a distinguished professor of energy and chemistry at UC Berkeley and co-director of the Kavli Energy Nanoscience Institute at Berkeley. He is known for his seminal work on semiconductor nanowires and their photonic and energy applications. And today he will speak about artificial photosynthesis. So Peidong, the pod is yours.
Thanks, Avner. First of all, I want to convey to our colleagues in Israel that our hearts are with you. We're all very, very much terrified for what's happening in the past couple of days. Please stay safe. So I'm going to directly jump into the carbon cycle that this morning the robot showed. Okay, where's it's this one?
Yes.
Okay. Okay. So I will mainly talk about how can we come up with a solution trying to fix CO2, in particular using photoelectrochemistry. There are several different ways to convert the CO2 back into chemical fuels. So basically, making these high energy density chemical fuels. I think tomorrow Ted Sargent probably will talk about another approach which is related to the PV plus electrolyzer approach. And today I will more focus on an integrated approach. And the integrated approach is really sort of based upon what's happening in natural photosynthesis. Essentially, it's mimicking of the natural photosynthesis. If you look at the natural photosynthesis, of course, we have 2 photons basically being absorbed and energy being basically used for water oxidation, give you oxygen, and also for the CO2 fixation. And even back now is almost 70 years ago, Melvin Kelvin is already thinking about how to come up with such an artificial photosynthetic system to fix CO2 using sunlight. Okay? And of course, this is a very, very challenging sort of scientific effort. It takes development of the suitable semiconductor, suitable catalyst to put them together, And that's basically in fully integrated system. The concept was proposed by Arthur Nozick at NREL. Again, in the 70s, it's called a photochemical diode. And within this photochemical diode concept, you will see that essentially we have two semiconductors. One is we call as photocathode, another one is photoanode. And basically we form two solid basic semiconductor electrolyte junction when we put this diode into electrolytes, and each of these junctions will give you certain photovoltage, and those photovoltage will be used to carry out the half reaction. On one side is at the beginning when Arthur Nozick proposes water oxidation and water reduction. So it's Arthur Nozick proposed this idea really for the solar water spreading. So of course, this concept similarly can be applied to CO2 fixation, which is actually for CO2 fixation certainly is much more challenging because we know the CO2 reduction itself have large over potential. Okay? But this is the initial concept, but experimental demonstrating this concept for water spreading for CO2 reduction takes actually several decades later. Okay? Okay, so I think the basic concept of this design started with the DOE efforts in the Helios program. And the Helios program is I think in the States, that's the DOE's first EFRC center. And then later on, you are aware of that DOE every year will basically award maybe 20 EFRC. And the Helios program at Berkeley is the first EFRC center. So at that time, basically, we put down this design. This is sort of artificial photosynthetic system based on a high surface area semiconductor electrodes integrated with two types of catalysts. One is reduction catalyst, another is oxidation catalyst. And of course, this is taking on some of the major benefit of these newly developed semiconductor nanostructure in the nanoscience. And this particular concept, you can consider this is essentially nanoscopic photochemical diode, and a million of them putting together. The basic concept was put on paper almost 20 years ago. Later on, this concept propagating into another much big energy hub efforts in the phase 1, phase 2 of JCAP, and then nowadays is sort of the energy hub split into two. One is LISA at California, another one is Chase in the East Coast. So overall, DOE has been invested on this thing about $300 million so far. Again, if we look at the sort of design principle, we have basically two photon Gaussian coupled with two half reactions. So there are many different sort of considerations. The reason we choose nanowire as our photocathode, there are two major reasons behind it. One is basically the nanowire photoelectrodes, you can basically orthogonalize light absorption charge migration, meaning sunlight photon goes in, and you are going to generate the charges, either electron or holes, and they can very fast transport to the surface to help you to make chemical bond. Okay, so that's one major advantage that the bulk semiconductor does not have. The second one is basically these high surface area semiconductor nanowires give you this matching, so-called matching the catalytic turnover frequency of catalyst with solar flux. Okay? We want to utilize every electron, every hole being generated from the semiconductor to making chemical bond. Okay? And from that point, basically we start to look into actually right now the workhorse photocathode, where all the reductions happening, whether it's water reduction or CO2 reduction, is the silicon nanowire photocathode. And by the way, they have also have the light trapping capability, meaning photon goes in, they cannot escape until they get absorbed by semiconductor. So that's another major advantage for this class of photoelectrodes. These are the high surface area electrodes. You can start to think about loading with different catalysts. And one thing I want to point out is many of these electrodes in the one-sound irradiation, okay, just similar to the PV photovoltaics, you can easily basically crank up 20 milliamp square centimeter in terms of current density. And that's basically the electron flux we want to utilize to do the chemistry. Okay? So that's 20 milliamp square centimeter in the one sound, that's the number you need to keep in mind. So the first fully integrated photochemical diode concept is demonstrated indeed in this nanowire version. It's a silicon photocathode, titanium oxide photoanode for the overall water spreading. Okay? Again, you will notice that for water spreading, you are seeing many of these sort of overlapping curves. One is a photocathode, one is a photoanode. And the cross point is representing the so-called bias-free operation, meaning that only with the one-sun irradiation, you don't need external energy input. And that's operating current for you to drive, in this case, is water reduction to generate hydrogen. Okay? So, of course, you want basically this cross point be as high as possible so that you can generate as much as hydrogen as possible in the one-sun irradiation. However, you can see in the hydrogen case, we can do so by changing different photocathode to photoanode. Of course, indium phosphide is not as stable as silicon. There is a durability issue still. But for this concept to apply to the water spreading, indeed, it's working. Now, if you want to utilize this concept to do the CO2 reduction, then we have issue. Okay? As we know, the amount of photovoltage we can generate from the semiconductor and the one-sun irradiation is limited. Those are 2 voltage added up. Okay? Typically, it's 1/3 of the band gap of semiconductor you are using. Now, if you want to run the CO2 reduction on one side, on the photocathode end, CO2 reduction, we know the electrochemically, their overpotential is 900 millivolts, 1 volt. Okay? So we really don't have that photovoltage to cover the thermodynamic sort of requirement in terms of the CO2 reduction, plus the other side is OER reaction, water oxidation, plus all the overpotential required for CO2 reduction OER. Okay? So that's the problem. However, this sort of shortage of photovoltage can be sort of rectified that by introducing a biological catalyst. Okay? And again, you are looking at here, this is the photocathode end, and this is the OER end. This curve basically shows you how much photovoltage you are generating. If you're using inorganic sort of CO2 catalyst, you will see this curve and this curve, there's no overlap. That means that essentially you cannot do anything under one-sun irradiation. Now with the biological catalyst, this can be basically solved. Okay? Biological catalysts, many of these biological catalysts, for example, some of these microorganisms, they can reduce CO2 at thermodynamic potential, almost with sort of 100 or 200 millivolts of overpotential, drive CO2 to C2. Okay? And this way, you can basically get this bias-free operation of CO2 fixation and the one-sun irradiation with OER on the other end. Okay? That's the sort of, again, of course, that states basically, well, putting out the one first very significant challenge in this field is we do need to come up with an inorganic catalyst with comparable overpotential like these biological systems. Okay? That's still, at this moment, we don't have such catalyst. Okay? Especially with sort of comparable 200 or 300 millivolts of potential. But a biological system, it works, and we have these microorganisms, whether you are looking at here is S. ovata or thermoacidica. They can take electron from our semiconductor directly, and of course this is a fairly complex so-called acetyl-CoA pathway that CO2 goes in, and there are multiple steps of this sort of chemical reaction. Every step is 2 electrons goes in until you make actual acetate, in this case, is C2 product with close to unity selectivity. Okay? Again, that's the challenge for the electrocatalysis community. Can we develop inorganic catalysts with overpotential of 200 or 300 millieV with 100% selectivity, okay? Mimicking these biological systems. Okay? And that's an open challenge at this moment in the electrocatalysis community. And we basically put together this integrated system, and this system basically can operate at basically bias-free. One-sun irradiation goes in, water goes into oxygen, CO2 goes to acetate. And the first generation operates at 0.3 milliamp per square centimeter, 0.3. Okay? Remember earlier on, I mentioned the one sign radiation, typically you need to get up to 20, so it's very low in the first generation. And the acetate, of course, as a general concept, once you have the acetate, you can do many of these sort of downstream upgrade into different product, like butanol or PHB or these Carol species. Okay? And that's basically all of these carbon now is coming from CO2. So that's the benefit of using this photoelectrochemistry and using photochemical diode concept. Okay? And the second generation, of course, we keep optimize the sort of loading of these catalysts, biological catalysts. We're now getting to 4% solar to chemical. Okay? So now the last 2 minutes, I want to quickly mention this photochemical diode concept again can be revised. Earlier on, I emphasized in order to mimic the natural photosynthesis, we have the second half reaction is always water oxidation. However, we know water oxidation is very sluggish, it's very energy demanding. And essentially the water here is our electron source. Okay? And this can be solved basically, again, that sort of bottleneck can be removed if we basically replace the OER with the water oxidation half reaction with some organic substance oxidation half reaction. Okay? And this way, actually, immediately you can remove that 1.3 volts of thermodynamic potential. Okay? Essentially, now the photocathode end, you can do the reduction, water or CO2 reduction. Anode side, you are doing, for example, alcohol oxidation or glycerol oxidation, or even you can do the sort of plastic PET sort of cycling. Okay? And this thermodynamically requires much, much less energy. All you need is 200 millivolts. Okay? So that immediately remove a big requirement in terms of photo voltage, and that give us actually the overall, with this sort of strategy, replace OER with a much sort of another reaction with much less energy requirement. That will give us the sort of the, again, in this case, you are now seeing actually on the photocathode end is silicon, P-type silicon nanowire. Photoanode end is N-type silicon nanowire. It's all silicon now. They can process at basically, you are looking at a 6-inch wafer here. Now this thing, actually, now you can do this and bias-free operation easily, getting up to approaching actually bias-free operation at a 10 milliamp per square centimeter operation to drive either water oxidation, water reduction, or CO2 reduction. Okay? And another major benefit is because now the photocathode and photoanode is silicon, and it's a sort of small band gap semiconductor, so the whole reaction now we can power with red light. Okay? And at the moment, we can basically power these photochemical diode with red light to drive water reduction, generate hydrogen, or drive CO2 to C2. That opens up a potential scaling up sort of possibility. Okay? And nowadays, we're basically processing these things at 6-inch wafer. Since we can power these things with red light, essentially now you can think about a sort of almost like a vertical form of CO2 reduction in-house. You don't need a sunlight in this case. All you need is solar electricity, drive a high quantum efficiency LED, red LED, and drive these. And they can operate at sort of this 10 milliamp per square centimeter to drive this water reduction and CO2 reduction. And with, of course, if you use these biological catalysts, you have almost unity selectivity. And of course, in order to improve on the stability, we do need, again, inorganic catalysts with low overpotential and high selectivity. And I will stop there.
So we move on to the next speaker, Professor Uri Banin. Professor Banin is a chemistry professor at the Hebrew University of Jerusalem. He is known for seminal work on colloidal semiconductor nanocrystals, and particularly hybrid semiconductor metal nanoparticles. Professor Banin will speak about the application of these nanoparticles in solar fuel production. Uri?
Yes, thank you very much, Avner. Indeed, I will talk about the photocatalytic hybrid semiconductor metal nanocrystals for solar fuels. So, just a minute. Yeah, this last week actually was a very euphoric week until Saturday, I have to say, for us in the field of quantum dots. The Nobel Prize in chemistry was awarded for quantum dots. By the way, do you see the full screen, or do you have this line on top? Just asking. Okay. Anyways, and these colleagues, which are good friends, and I've been working with them for a long time as well, have allowed our quantum dots. We're quantum dot pioneers. But then on Saturday morning at 6:30 a.m., waking up, I opened the radio and I heard so many of these rocket alarms, which unfortunately was not so unusual, but immediately we had also a siren here near Jerusalem. And then we learned of the horrific situation that we encountered. As Avner said, we shall prevail, and I would like to thank you for the support and for still maintaining this workshop. And with this starting point, of course, colloidal quantum materials are much more than quantum dots. Over the years, we've been able, as a community, to achieve control over shape, like nanorods, nanoplatelets, heterostructures. And the advantage of the quantum dot approach is, of course, the ability to tune properties, the emission color being the most obvious one through quantum confinement. And indeed, these materials have made it into real-life application on millions and millions of scale of displays. So here, if this is the chart representing our vision, then with the RGB approach, we can cover in usual screens only this part of the color chart. But with quantum dots simply integrated into the backlight unit, we can achieve much greater color coverage. And those are the screens with a Q. I've had a startup company in this field, Q-Light Nanotech, which became part of Merck. And also there is a full roadmap for further implementation of these materials in the display field. The thing that I want to emphasize for our field in this sense is that we have the opportunity here to see that this complex synthesis, so to speak, could be upscale in an economical scale. And I saw a 3,000-liter reactor for quantum dots for these applications. And with very precise control over the color, over the size, with unity quantum yield, and also basically the stability requirements are extremely high for screens. And so the next step is really to take this to also into other applications, bringing me to be optimistic that we can do that. And well, when we want to use it in a screen, we start from exciting right now optical excitation in the blue of our electron hole pair, which relax and then recombine red or green colors based on the particular characteristics, which brings us to the display. If we want to think about using this for photocatalysis, we need something else, which is to separate the charge. The first step being absorption, but then we want to separate charge. And we can do that, for example, when we have a semiconductor metal hybrid particle, which will then also facilitate the ability to do redox reactions, especially as we have a natural catalytic island in the form of this metal particle. The reactions I've been focusing on are mainly so far water splitting, but there are other photocatalytic applications for us, less relevant for this meeting, but of interest, such as in photoinitiators, water purification, etc. Now, I started off with these semiconductor metal particles back in 2004, and this has expanded by work of the whole community and our work as well into various ability to control the growth of different metals, different type of growth, different semiconductor particles with different shapes and compositions. And so based on this, this has really emerged into one of the characteristics of this charge separation and photocatalysis, aiming at water splitting. There are several groups that have been working in this topic, like Lila Hamirav at the Technion, started this off with Alivisatos when she's doing great work on her own, our own work here, work of Jochen Feldman at LMU, other colleagues like Tim Lian, Todd Krause around the world. And what I want to share with you is the approach that we have. First of all, is a reductionist approach to understand and study the physical chemistry. And Robert, here I share your passion as a physical chemist to these type of studies, to understand fundamental aspects of, let's say, design principles for such a photocatalyst. And the first question I'll give an example of is the effect of the metal tip size, the co-catalyst size. The model system we used are cadmium sulfide particles with gold. And we have the ability first through our synthesis to control the size very nicely, initially nucleating a small tip of gold in the dark, and then with under illumination, the photocatalytic action already allows us to grow selectively this one metal tip larger and larger. And you can see that this is a plasmon response which emerges along with the semiconductor band gap. And then we can go ahead and measure the hydrogen generation. It's the half reaction of the reduction. And what we discovered was a non-monotonic behavior. Namely, there is less hydrogen reduction in the very small tips, which then maximizes out at some intermediate size and then reduces again. To understand this, we have teamed up with Professor Eran Rabbani to model this, and also with Professor Julius Cerullo to help us measure the charge separation dynamics. And if you think about it, there are two steps in this type of process. First of all, the charge separation step, and then the reduction step. And in the charge separation step actually is actually coming about to depend strongly on the size based on essentially the density of states of receiving gold particle, which receives the electron here. And this explains this type of rise dependent, this rise of this side of the model of the expected quantum yield. The next step is the reduction, which based on the Butler-Volmer equation is actually depending on the size on an opposite way. As we make the particle larger, the Fermi energy of the gold is being reduced, and we cannot actually transfer charge to the water. So that brings about this kind of sweet spot, and that is something we've learned through this kind of study. Now, this is the result for cadmium sulfide gold. Since then, other people like Lilach Amirav have found a similar behavior, although their explanation is somewhat different for cadmium sulfide nickel. Palladium, it's hard to see, but also shows an intermediate size, which is optimal for this type of reduction. Cadmium sulfide platinum, published by Tim Lian, is he reached up to 3 nanometer diameter, so there's a maximum of 3 nanometers. We don't know what happens beyond that. So we see that that type of reductionist approach is very important. And most recently, we also discovered a different regime, which is well known in catalysis, and this is a single atom catalyst limit. Now I'm shifting over to another system, it's zinc selenide, again with gold. We found that in very low concentration of gold added to the reaction, we could identify by electron microscopy these spots, thanks to the advancement in electron microscopy. And the validation is again provided by use of additional techniques in collaboration with Professor Anatoly Fenkel. X-ray absorption spectroscopy can give a signature for the gold chemical environment. And we can see very clearly a very big difference between the zinc selenide the gold signature in the very low limit of the single atom catalyst versus the case when we have these tips. So this establishes that we then indeed have a single atom catalyst limit here for photocatalysis, which then brings about a very sharp behavior at the single atom catalyst limit. When we normalize it per atomic site, which is a conventional way of presenting single atom catalyst behavior, we do see a range in which we have specific quantum yield which per atom, which then decreases when we go into the TIPS regime. So why should we like this regime? which has been studied quite extensively in other forms of catalysts, not necessarily in these type of quantum rod systems. It's the ultimate size limit, of course. So it's the maximal utilization efficiency you can hope for in your co-catalyst, which is a good material use. We need to have strong metal support interaction to prevent aggregation of those single atoms on the surface. And there is a potential for high activity and selectivity, not necessarily for water splitting, but for other photocatalytic reactions. Another type of fundamental study I want to highlight is the combination of excitonic and plasmonic photocatalysis and the role of resonance. So here is the plasmon, here is the exciton in this cat sulfide gold system. And usually we can utilize the light within the semiconductor absorption. Whatever is absorbed in the plasmon here is decaying so fast, we could not do too much with that energy. We lose this energy to heat. But in cadmium selenide gold, there is a resonance already between the semiconductor band gap as well as the plasmon resonance. And we can see here some results from Team Lian. So here you do have this range, even extending out all the way to the near infrared, which would allow you perhaps to harvest more photons. And in that study of Team Lian, the mechanism that he suggested here is called plasmon-induced charge transfer, namely absorbing in the IR actually brings about an electron turning back into the semiconductor, which you may utilize, meaning that you can expand your absorbed photon efficiencies in terms of the spectrum to utilize for efficient photocatalysis. And this is an interesting observation. We went ahead and have looked into this to set the limits of this in order to use it in photocatalysis. And what we discovered was that actually we do have this PICT, which is immediate type of excitation into the semiconductor, but there is also the usual process of electron transfer from the semiconductor to the gold. So namely, there's a back transfer, which also occurs on a very rapid time scale in this system because of the resonance of 200 femtoseconds. So your time window for utilization of this charge, you have to trap it in a very fast time, but at least it gives us the idea what is needed if we want to harvest this light in order to separate the charge. Okay, now thinking ahead, how would we go ahead and not just use this as a free catalyst in solution and thinking about just a half reaction? Even full water splitting, one approach could be to have an oxidative island on one side of this nanorod and a reduction site on the other side. But the merging of the nanocrystals with a photoelectrochemical cell is a point which we would like to explore. And for that purpose, we have a collaboration with Professor Meni Shalom, who works on, from Ben Gurion University, working on carbon nitride type porous photoelectrodes. And those are photoanodes typically, where we want to merge these two systems together to benefit the advantage of both of them. And indeed, through this collaboration, this is a flat electrode, not a flat, a porous electrode of CNGO, carbon nitride with graphene oxide, which Meni Shalom can prepare. With electrophoretic deposition from solution, we've demonstrated the ability to load it very efficiently with our zinc selenide nanoparticles, nanorods, just as a model system initially. But this type of approach can be expanded to other type of nanoparticles. And what we saw indeed in the photocurrent response, that doing so, we have been able to increase by about 75% the current densities for the photoanode here. And this is accompanied by increased oxygen production owing to the tandem operation and the charge separation occurring at the CNGO zinc selenide interface. And so this could be a way to utilize these type of nanocrystal-based photocatalysts in a system which will already separate the two half reactions and take advantage of the ability to combine the photocatalysis with electrocatalysis. So I'm reaching kind of my summary here. I've shown you the aim to continue with design rules, and this is something I would like to continue with, and we should continue with, given that such a system has so many parameters. We need to look for the heavy metal-free materials for such type of photocatalytic applications. We can and are looking for new materials. I've shown you the single atom catalyst regime. We have this ability now to look into combining two different nanomaterials into a dimer. We've done that with two semiconductors, and now we are expanding that also for photocatalytic systems, not just for emitting dimers, but also for photocatalytic dimers, which may separate charge, which you might consider as an analog on the nanoparticle level of the p-n junction that was presented so beautifully by Peidong. And we want to do more fundamental studies, and Beatriz will touch on that, I'm sure, but this is aimed to correlate structure-function relations and the ability to actually measure the photocatalytic activity of even a single particle, and then look at that very same particle with electron microscopy is something that we have been starting to do first for the optical properties, but also have the idea to do this also with the photocatalytic particles to gain the ultimate information. Where do we want the metal, for example, etc. The photoelectrochemical approach, which I've shown you one realization of. Actually, we had another one with Avner before, but the photoelectrochemical approach, I think those two types of systems of porous electrodes and the semiconductor metal and semiconductor nanocrystals could be a good match. And the idea of a full reaction cycle that can consider also production of valuable chemicals and not necessarily the water splitting is also another important direction. Now, we've seen the history of the field by Peidong, and indeed, when I think about how long it took us as a community to get televisions out from quantum dots, that was 30 years from the synthesis on which Munji Bowendi received, let's say, the Nobel Prize just last week. 40 years since the first attempts or thinking about quantum dots, where Ekimov and Bruce did major contributions. And, you know, it took us until about a little over a decade ago for the first screen to come out with quantum dots. And now I don't think we have enough time for trying to get the next effort. So I want to emphasize two things. One is really the importance of cooperation. And in that sense, I think this trilateral meeting is a very important platform. In my case, we need cooperation in the ultrafast part. I have a good colleague for that, Julia Cerullo from PolyINI, the theory and modeling, Eran Rabbani, the photoelectrochemistry, being Avner or Meni Shalom. And this is something that is essential. And well, I've recently seen on cinema Oppenheimer, the movie Oppenheimer, and you know the Manhattan Project. Okay, could we set up something like that without barriers to really push forward solar fuel generation to speed up a viable solution on the timescale that we needed? And with this, I will stop. Just thanking my group from a recent group trip, the funding agencies, and again, the corporations. Thank you very much.
And now we move on to the third speaker, Professor Beatriz Cuenya. She's the director of the Interface Science Department at the Fritz Haber Institute of the Max Planck Society in Berlin. She is known for her groundbreaking work on the understanding of catalysis, in particular electrocatalysis, in energy conversion applications. Professor Cuenya will speak about the dynamic behavior of surfaces and interfaces during electrocatalytic processes. And Beatriz, the pod is yours.
Thank you. Thank you very much for the introduction. And I'm actually very sad that we cannot meet in person. So my admiration to my Israeli colleagues that are still online following this meeting despite the very difficult circumstances. And I hope that all the people that are missing can be brought home soon and that this terror is ended as soon as possible. I will be starting talking about water splitting, and my idea was to tell you something about the material science and what is needed. So we have seen this morning the examples of electrolyzers, large scale, and just to give you an idea of what we are talking about. So we need about 10 tons of water, clean water, to get about 1 ton of hydrogen. And then, of course, we need to be able to store it and transport it. And as we spoke before, ammonia could be one of these energy vectors. However, if we are talking about how slow is the technology transfer, you can read what Jules Verne wrote in 1874. So this was a science fiction novel, but the technology was already there. The discovery of water splitting was already there. So he was writing, water will one day be employed as a fuel that hydrogen and oxygen, which constitute it, used singly or together, will furnish an inexhaustible source of heat and light of an intensity of which coal is not capable. So if we are concerned about 30 years to move forward technology, think about the poor people that were doing the investigation in water electrolysis back then and that they couldn't see this in practice. Now we can. So as we know from water electrolysis, so we have the reactions happening at the anode and at the cathode. And at the anode, we have the oxygen evolution reaction that is the hardest thing to do. So we have thermodynamically 1.2 standard cell potential for water splitting. And there is a sluggish kinetics, and we need an overpotential. And what we know very well is that there are certain materials that can be used as catalysts for this reaction. And the also realization is that there are several technologies that are competing in this field. And one of them is based on acidic media. And this is using expensive metals, for example, in this case, oxides of iridium. And the other one is the alkaline technology that is using much more cost-efficient materials. So the idea of which technology will be for the future is basically related to everything that we discussed today about sustainability, availability of materials. So if we really want to make an energy transition based on green hydrogen, and we see how much iridium we have in the world and how expensive it will be very difficult to justify this. So talking about the materials, I mentioned that for the alkali technology, metals and metal oxides, like including nickel and cobalt, are used commonly. And what we know by now is that people try to work with many different structures of the initial pre-catalyst. And we learned that under reaction conditions, these materials transform, and it makes something called a cobalt oxyhydroxide layer. And actually, no matter how you start with, you're going to see this transformation. But I will show you later today that actually the initial structure will influence how this transformation is going to happen, what will be the characteristics of the surface layer, the thickness, the defect density, and this, of course, is going to affect the performance of the material. So it was mentioned before that it's very important that we can control very well how we synthesize our materials. This is the pre-catalyst. I'm mentioning right now that under reaction conditions, we change the material and we make this skin layer, this oxide hydroxide. But even more important is that if you stop the reaction conditions, you can get back to the initial material or to another material that is actually not the active phase. So this brings us something very important, that we need to do characterization with microscopy and spectroscopy under operando conditions, and under the conditions as close as possible as what will be the final use of the material. Just to show you an example. So this is beta cobalt hydroxide materials. These are very thin platelets. And by now, we can put them in an electron microscope. This is an electrochemical transmission electron microscope. And even this initially well-defined material is experiencing very drastic transformations. If you are looking in this regime, you're going to see the solution. You're going to see the formation of these small particles. There is mobility of these plates. So if we really want to understand and actually rationally design a catalyst, we need to understand what is happening in the reaction conditions so that we can tune this, what we can change, the pre-catalyst, catalyst, so that we will come up under reaction conditions with a material that will be in the most active state. And of course, stability is going to be very important for the industrial level, so we need to work on this in this field as a very important point. So I wanted to give some examples. I wanted to give some examples of typical materials that are being used for oxygen evolution reaction. And these are, again, starting with cobalt oxyhydroxide nanoparticles. In this case, these are cobalt. And the question was, is there anything that we can do to improve the activity? For example, you decrease the particle size, we could see that we can improve the activity, mass, or a specific activity. And then having these relatively well-defined systems, we can start looking at the active state formation under reaction conditions. And we realized that in this case, this is done at the synchrotron with X-ray absorption spectroscopy. You can see that the initial state, the activated state, and the reaction state, the operando state, looks very different. Just by eye, you can see that there is a change here. And from this type of measurements, we can learn, for example, as a function of the particle size, what will be the oxidation state of this material, and even the surface termination. And so we can conclude, for example, that on these type of materials, you don't have a very large oxidation state of cobalt. What you have under reaction conditions is the formation of these oxyl species. So a lot of detailed understanding that can be achieved right now using spectroscopic methods under reaction conditions. To continue with this, so we know that in the industrial catalyst, we don't only have normally just a metal oxide. We normally have a mixture, and sometimes we have contamination under reaction conditions. And for example, for OER, one of the common contaminants that you will have in the electrolyte is iron. So we decided to try to investigate in a controlled way, making on purpose mixed oxides, and also trying to add the iron as impurities from the electrolyte and try to understand what will be the structural changes and how does this affect the performance. So we have right now the possibilities of make this type of model systems. This is one of the oxides. We can study them with spectroscopy and microscopy methods quasi in situ or even operando, as I showed before. And even the model system, this is a perfect thin film of iron oxide, and we can make also, of course, other materials. You can see here this looks nothing but perfect, so you see defects there. And so there's going to be a lot of important structural details that you will need to know, and this is the pre-catalyst. Now we go to the real material under reaction conditions, and this is just a cobalt oxide thin film. This is how it looks with one of the facet orientations. Now we put it under reaction conditions, and you see the surface is changing. You see the formation of these small clusters there. So this is here the active state when we start making this oxyhydroxide layer. This is an operando measurement with an electrochemical AFM. And what we wanted to investigate was actually, does it matter how we make the pre-catalyst? So if we have exactly the same thin film with exactly the same thickness, and we have this termination, 001, or this termination, does the structure it remains the same or not, and does this affect the performance? And you can see by eye that here the catalyst apparently looks much more stable than this one that shows this transformation. But when you look to the electrocatalytic performance, in particular the onset potential for OER, this one that was showing these transformations under reaction conditions is more active, and it's also going to be more stable. So importance of this type of characterization is key to rationally design what we make as our beginning catalyst, even though we know that it will change. So I talk about impurities, and this is an example also for water splitting catalyst, in this case a nickel oxide catalyst. And our idea was to start adding the impurity, in this case iron, from the electrolyte. And we could see that if we start adding a little bit of iron at the beginning, we start improving the performance of the catalyst. But if we add too much iron, we poison the catalyst. So you can see this electrochemically, but you can also follow this with operando microscopy. So we can look at our structures, the morphology is changing, and if you see here in nickel is in pink, in iron is in yellow. And you can see that when the catalyst is nicely active, you have only the incorporation of iron to the surface of this nickel oxide, and it makes this double oxyhydroxide layer. And however, if you keep having too many impurities of iron in the electrolyte, then you don't go more into the bulk of this material. It actually starts to accumulate on the surface as iron oxide clusters, and this kills the performance. So with this type of operando microscopy experiments, including also spectroscopy characterization, you can start seeing actually when do I have a promoter and when do I have a poison, and you can tune this just by bringing these elements from the electrolyte itself, as you will have in an industrial setting. So just to show you a comparison, whether does it matter what you start with, if you start with the same crystalline orientation, again, very thin films, and you compare iron oxide, cobalt oxide, and cobalt iron oxide with different concentrations, at the beginning, the cobalt oxide was the best catalyst. However, under a couple of hours of electrochemical reaction, in this case OER, the cobalt iron oxide was much more active. And actually, it matters how much of cobalt, what is the cobalt to iron ratio. So with this, again, this type of system shows you that knowing very well the pre-catalyst doesn't give you the whole story, and that actually these investigations, and including the performance under reaction conditions, are key to understand water splitting phenomena. And so with this, I came to my take-home messages. So the synthesized materials are pre-catalysts, they are metastable, and they adapt to the reaction environment. And however, the structure of the pre-catalyst that you synthesize influences how it adapts to the reaction environment and what will be the operando transformation that you are going to observe. And very importantly, the active state of the material is formed during the catalysis. So if you want to understand the material and you want to be able to rationally design an electrocatalyst, you need to be able to do characterization under realistic reaction conditions. And only when you get this type of rational catalyst design, you are going to be able to improve the material's stability and, of course, also to decrease the process cost. And when I'm talking about realistic characterization, this means also working with the industry and trying to get and to understand these materials and the performance of these materials under the harsh conditions that you will have in this large-scale electrolyzer that I showed you before. So we have significant collaboration with the industry in this aspect. And something that I also hope that I could feature today was that small amounts, trace amounts of metal impurities on these metal oxides, they will tune the local structure of the active sites in morphology and electronic structure. And they're actually going to be key to understand degradation, for example, of the performance or even the promotion effect. So it depends on very, very minute changes, for example, in the impurity level within these electrolytes. And finally, Albert Einstein said something that I think applies very well to my field. Everything should be made as simple as possible, but not simpler. So these materials are very complex. So even if you make a model system to try to represent some features of the material, this model system is going to have a very large complexity. And of course, you need to investigate it under the real environment. So I'm here on behalf of my research department at the Fritz Institute, and I will be happy to be part of the discussion.
We move on to the fourth speaker, Professor Valerie Karplus. Is a professor in the Department of Engineering and Public Policy at Carnegie Mellon University. She is an expert in decarbonization of global corporate and industrial supply chains, regional approaches to low carbon transition, and the integrated design and evaluation of energy, air quality, and climate policies. Professor Karplus will speak about the challenges of using hydrogen to decarbonize iron and steel production. And Valerie, is your pod now. So
today I'm going to step back and kind of zoom out relative to the presentations that you've just heard. I have to say, though, that I am delighted to be on the same panel with those who are focused at the level of artificial photosynthesis and at the molecular level, which is to some extent where I started my undergraduate studies. And if you told me I would have sat on a panel with such distinguished scientists right here, I would have been very happy at that time. Now, my work today that I'm going to talk about is really focused at the integrative level when we think about energy transitions. So reducing CO2 emissions from energy and industrial systems requires working on multiple fronts. It's not just about the technology and the infrastructure, although those are critical and important, but it's also about getting the policy decisions and the institutions right. Organizational design is important, and thinking about how to manage the labor force transition and the community implications of the decarbonization at the scales that we've been talking about here today and over the past few days. So I'm going to be talking about work predominantly from two projects, and one is very new. So the first one is just over a year old. It's work of essentially 5 institutions, including Carnegie Mellon, spread across the world, connected with 2 universities, actually, in Germany, the Technische Universität in Dortmund and ZIW Mannheim, with focus in each of those on the engineering and the economics, respectively, of industrial decarbonization. We also have colleagues at Tsinghua University in China who are also energy systems experts, also working on policy design there. And then in South Africa, looking at sort of the local conditions around decarbonization, specifically in developing country contexts at the University of Cape Town. And so this is a partnership that has been funded by the National Science Foundation's Partnership for International Research and Education, and we call it the INDABA Partnership, or Industrial Decarbonization Analysis, Benchmarking, and Action, because the word INDABA also means bringing people together from diverse fields to talk about important issues. And indeed, this is a partnership that we have recently started, but we are very excited to grow, and is focusing mainly on the challenges in the industrial sector around decarbonizing process emissions and industrial heat. So that also ties very closely to the second project that I'll speak about, which is work funded by the Department of Energy recently, looking at the process of making direct reduced iron as part of the steel making process, using high blends of hydrogen between 90 and 100%. This work is pretty exciting, in part because it is taking place in partnership with 2 industrial companies in the United States that have not traditionally worked together. You might recognize the U.S. Steel Corporation as one of our oldest corporations in the U.S., and Nucor as the challenger electric arc furnace steelmaker. And with the strong support of these partners, and with my colleague at Carnegie Mellon University, Chris Pistorius, in the Material Science and Engineering Department, we are forging, I think, a truly interdisciplinary and cross academic to industry collaboration to move these processes from the TRL level 4 to 6, but importantly, I think, to publish the findings in the peer-reviewed literature and look at a number of issues that haven't been fully solved as we move to high hydrogen blends in steelmaking. And so I should say that both the work of the INDABA partnership and this project are very much focused at the moment on processes for reducing CO2 emissions from iron and steel making, but with the hope and the intent of taking some of these lessons out into other industrial sectors. Particularly, I was fascinated by the work described in the chemicals industry and in the cement and food and beverage sectors as well. So even low temperature heat applications are still well within scope. So I'm going to focus today on iron and steel making, and I'm going to show you 2 sets of insights, partially about the impact of policy, as well as kind of the techno-economic analysis we've been doing, and give you a flavor also. I think Jay Apt mentioned the importance of co-benefits in the low-carbon transition. I'll show you a little bit of work we've been doing there, and then also talk a little bit about the workforce implications of the transition in iron and steel making, which accounts for today about 7 to 9% of the world's CO2 emissions. I'm going to be just, so that we're all on the same page, I'll just briefly describe the technologies and then go into some results. I'll also, if there's time, show the results from a survey that we recently did of industry partners that represent 25% of global steelmaking, who recently attended a workshop and responded to a survey. So to give you some additional context for how a set of global steelmakers is thinking about and responding to these topics. So for most of history, steel has been made through the integrated route. This is using iron ore to produce iron today in a blast furnace, and using the basic oxygen process to refine steel. This route is, on average, relatively high in emissions and accounts for 72% of global production today. As scrap supplies increased, we have been using electric arc furnaces increasingly, and especially in the United States, this accounts for a large share of steel making there. the direct reduced iron pathway offers an opportunity to displace pig iron as a partial component of the EAF charge and reduce carbon dioxide emissions. But ultimately, if scrap supplies become limited, this route will need additional sources of virgin iron, which could take the form of direct reduced iron. And this is where the possibility of using hydrogen in large quantities to produce direct reduced iron, with hydrogen being the reductant, leads us to discuss the technology of interest today. I should also say we've been doing some analysis and considering the potential role of electrolytic iron making, so connecting back to the themes of this panel. We consider this as still quite pre-commercial, but promising. So just to give you a sense of sort of our starting point. So we did some analysis in the Indaba partnership looking at where we are today with the blast furnace. And so this is giving you, actually these bars on the left-hand side are every blast furnace that is currently operating in the United States with the composition of reductants averaged over the years 2011 to 2021. As you can see, there some coal, coke oven gas, and natural gas complement coke as the main reductants in the blast furnace process. If we look at the emissions, scope 1 emissions associated with those processes using a mass balance approach, you can see that there is actually quite a bit of variability within each of these furnaces at the furnace level, up to 15% above or below those mean levels. And the differences, I think, underscore the importance still of using every method available to operate this fleet as efficiently as possible, going even beyond the efficiencies that are being achieved and spreading those lessons more broadly within the fleet. Now, if we think about advanced routes, we're showing here the results of some techno-economic analysis that looks not just at DRI per se, but tries to sort of bound the envelope of both cost and emissions associated with each of these routes. And I realize this is a bit hard to see on the screen, so I'll just talk about some of the key findings that we have here. First of all, the basic, the integrated route, the blast furnace basic oxygen furnace route is shown, the first bar with the bars comprising the scope 1, scope 2, and scope 3 emissions totals. You should read those off of the left axis, and then the costs are indicated, is this variable cost only indicated by the black dots. So the integrated route and the EAF route with 100% scrap are shown with the two red boxes by way of comparison. Those are essentially our base case or today's technologies. Now, as you look at the other routes available, you can see that adding carbon capture and sequestration significantly reduces emissions from the blast furnace, but does not by any means eliminate them. So you still have 90% capture rates. You have many other points of emissions at these facilities, but indeed, that is one option. If you look at the DRI pathways, which include 100% natural gas DRI, the fourth bar over, 100% hydrogen DRI, and a flexible operation of both hydrogen and natural gas to make DRI, you can see that you have, in each of these cases, the cost and the emissions profile depends significantly on your use of hydrogen. And the assumption here is that we're making hydrogen with electrolysis, and that all of these, and that is coming from zero carbon electricity. Now, to be consistent, we have assumed that hydrogen, CCS, and molten oxide electrolysis, which is not shown here, are only used if sufficient zero carbon electricity is available. So if we go to the next slide, you can obviously see how using grid electricity for any of these pathways, and this is showing emissions, significantly increases your scope 2 emissions. And to the point where you're using the electric arc furnace route with DRI means that you're starting to approach the emissions level of some of today's best available technologies for blast furnaces. And so in that case, you could argue that if you're able to operate with 100% scrap, that's great, or high percentages of scrap, if you can do natural gas DRI, you might actually be better off on both emissions and cost in this scenario. And so it's really important to keep in mind the implications of not being able to use zero carbon hydrogen when you're comparing these technologies. Next, I wanted to just show how the Inflation Reduction Act, which is one of 3 major pieces of legislation in the United States that are aimed at advancing, in part aimed at advancing the energy transition, are having on the perceived costs of these technologies for industry and in potentially shifting decision-making because of the change, the impact that those have on those perceived costs. So I'm showing here the costs of the different routes. So again, on the far left side of the graph, you can see the integrated pathway compared to the 100% EAF scrap pathway. That's today's variable costs. If you look at the hydrogen, now shifting to the interior of that box, those are the pathways: hydrogen DRI, partial use of hydrogen in the DRI furnace, and 90% CCS on a flexible hydrogen-based DRI. So this is a setup in which you're using the CCS when you're using natural gas as a reductant, and when you're not, then you're essentially using hydrogen. And so you're either operating on one or the other. You're not blending. You could look at other cases. But basically what you're seeing in general, what the Inflation Reduction Act does is it lowers the cost of producing with hydrogen significantly, to the point where it now is the slightly better option compared to the CCS pathway. So the Inflation Reduction Act tax credit, specifically 45V, which offers you $3 per kilogram of hydrogen, puts hydrogen on much more equal footing with the CCS option. And that's also true when you look at the blast furnace route as well. At the same time, the Inflation Reduction Act does not provide dynamic incentives to work on other advanced process routes for electrolytic iron making, for example. And so thinking about whether we really want to be spending this much to support hydrogen, specifically when that's just targeting the variable cost side of things, is a question. Now, as we move to defossilized processes for iron and steel making, there will be some implications for the workforce. And you'll see in a moment that industry doesn't seem to place that as high on their list of things they're concerned about. But this is something, of course, that we're very interested in understanding from a scientific and sort of technical perspective. So we've looked actually at quantifying skills involved in current iron and steel occupations that are likely to be disrupted in a transition. And so specifically, these include first-line supervisors of production, operations workers in iron and steel, laborers working in freight moving, material movers, machinists, et cetera. And so each of these graphs represents a different occupation. And what we've done is looked at how well the occupation, this is just for Southwest Pennsylvania, where there is an operating integrated steel mill, and asked whether those occupational skills map, and it's actually not just skills, but knowledge and abilities. So there are different metrics, and we use text analysis and similarity measures to look at the match between the requirements of the jobs in the existing industry and the jobs that are being held by the local population in Southwest Pennsylvania, so that full universe, which is around 700 different jobs. And what we find is that some occupations are very likely to transfer. So for example, on the bottom left, you can see that transferability is fairly high for a whole range of skill similarity thresholds. So that's the because you can see the curve dropping off more towards the right. But then if you compare that to the one on the bottom right, the skill similarity, the curve drops off precipitously at an earlier point, so a lower level of skill similarity. And that's, I think, kind of, those are the specific positions, workers, what you might target for training programs and for, and also for additional assistance, both for them and for their families in the course of an energy transition. So being able to have this kind of analytical perspective on how those jobs may, what those will happen to those workers when those jobs may be under pressure is important information that policymakers are often interested in. At the same time, they're also interested in the co-benefits, and I think this is just one very brief illustration of the observations of how air pollution, we're focusing here on fine particulate matter, PM2.5, change as you move away from a specific furnace. The blue are the integrated facilities. The pink are the electric arc furnaces. As you can see, there's not very much PM2.5 associated with an electric arc furnace, as expected, compared to an integrated facility. As you move further away from a facility, that the difference between the two declines. We're essentially showing it as a difference in difference. We're also seeing potentially these deltas are essentially of the same magnitude as the impact that the Clean Air Act had over multiple decades in the United States. And so we're going now to look at the impacts of past closures on air quality in local areas and think about just how to incorporate that and display that alongside the carbon implications and the jobs implications of these investments. And so this goes back to kind of the thing where I started, which is really that you need to work these problems on multiple fronts in an integrated way and think differently across disciplinary boundaries in order to advance solutions that are workable in the real world. So, and on that note, I thought if there's time, and maybe there's not, I would share some results from an industry survey, but let me just do a quick time check, because I know we're pushing. Okay.
Avner had to.
All right, we'll keep this short. I just have, I think, 4 slides. So.
Avner had to go to the shelter. There was a siren in Haifa.
Okay,
no.
Thank you for letting us know.
Okay.
Yeah, this is the reason he's not here at the moment.
Shall I continue?
Yes, we will continue. I will take over now.
Okay. Okay, I hope, yeah. Good. Okay. So let me just quickly give some context here. We had a meeting at Carnegie Mellon actually just last week. And as part of that meeting, we surveyed the attendees, which represented 20 global steel companies. 1 or 2 of those companies had operations in, 2 of those companies had operations in Europe, but many of them represented much of the production in Asia. China accounts for 50% of global steel production. So we had 2 companies that accounted for roughly 10% of that. So that's who responded to this survey. In total, we had 20 companies, again, represented. Now, I thought that this was a nice quote that indicated kind of where this meeting started from. So no discussion of whether climate change was real. It was much more, now that the direction of decarbonization has been decided, I hope that discussions on how to effectively decarbonize will take place. And so that was the spirit in which this meeting really proceeded. Now, we asked companies, which technologies or strategies are your organizations pursuing to reduce greenhouse gas emissions from your operations? And by far the most popular, and almost every company responded that had integrated operations responded that operational efficiency of the blast furnace was the main focus. If we look at direct reduced iron, there were 9 companies. More companies were producing DRI with hydrogen than were working with natural gas, and 5 of those companies were focused on both. So again, operational efficiency. After that, there was a focus on shifting to electric arc furnace production, which I think is, and then certainly there were a number of other strategies given as well. We then asked them, how would you prioritize research and development funding across different technologies or strategies? And 70% of the respondents really focused on the importance of operational efficiency. The second bar is produce DRI with hydrogen, produce zero CO2 electricity, so or procure zero CO2 electricity, which I think will be an increasingly difficult challenge as competing demands for that electricity emerge, and then increase the share of electric arc furnace production, as well as the next one is produce hydrogen for iron making. So that accounts for all of those that at least 40% of the group gave those as high priorities. And if we look at reporting, among these 20 companies, again, including India, South Africa, Korea, Japan, China, Australia, these companies, and American companies, all of the major American producers were represented. All of them are now reporting essentially scope 1 emissions if they were actively making steel. Scope 1 and 2 was reported by all but one of those, and then most companies are moving towards reporting scope 3. All of them are measuring it, but in terms of reporting, a growing number are now feeling that pressure. They're measuring GHG emissions at very different levels, and this is actually one of the most challenging problems that emerged potentially for international conversations on this topic, because of the need to translate from the firm to the plant to the production process level and sometimes to the product level. Under different regulations, companies expressed challenges and concern and desire to have single reporting boundaries and accounting standards. And then finally, when we asked companies how important were each of the factors below in limiting investments in green steel production, they pointed to the lack of supporting infrastructure, the lack of investment funding, competitive consequences, political will, and lack of technical solutions as being either extremely important or very important. It's up to 70% roughly of the respondents. But workforce needs and community needs, which are the last two bars, were very, were ranked as slightly important or not important by over 40% of the respondents. Now, companies had very different reasons why they were sort of driving defossilization within their organizations, whether it was incentives from current policies to the drive from customers to competitors' decarbonization moves to CO2 taxes to internal company strategy to absolutely none. I don't know if that means altruism, but it was really interesting to see what people sort of freely shared with us. And this is just a snapshot of what we learned. When it came to mechanisms for accelerating green steel production, many highlighted options that had the word tax credits in them. So whether it was green steel production subsidies or tax credits, buyer pledges was number 2. Investment subsidies or tax credits and hydrogen production tax credits, all of those were kind of ranked in the top 4, and above 50% highlighted them as important. So this is just now to wrap up. Let me say first of all that the tax credits under the Inflation Reduction Act seem like they would cover much of the variable cost of the steel transition via hydrogen or CCS, but they do omit many options and don't cover the capital costs, which beyond the first few demonstration projects. So they're very piecemeal compared to some of the approaches I've heard described in Germany. There seemed to be openness among the industry representatives to green steel production tax credits or even a CO2 fee in the United States, especially if the revenues could help to offset those capital costs for the transition. And then finally, our analysis suggested that natural gas DRI is actually maybe not a bad route to be pursuing with the flexibility to move to hydrogen or add CCS. And then finally, beyond technology, we've learned that many our stakeholders are very interested to see the local air quality and workforce implications of these investments beyond just the DOE, and these can form an important part of community conversations and also with state governments and local stakeholders more broadly in developing greater confidence and understanding about the implications of these investments. Thank you.
Thank you very much, Valerie. And Christopher is with us from the Fraunhofer Institute for Solar Energy Systems in Freiburg, Breisgau in Germany. And he, I mean, today we started with the global perspective with Mary Burst-Warlick And we are going to end with a global perspective on one of the topics that today I heard like 1,000 times, and this is hydrogen. And Christopher, the floor is yours, please. Let's try to focus on 10 to 15 minutes maximum, please, if it's possible.
I think all evening is ours. So thank you very much also Anna for squeezing me into this last session. Indeed, tomorrow I would have done this out of the train, and that's very unstable. I would like to give a global perspective on all these hydrogen topics. So it's a nice wrap up also between electrons and molecules, I would say. First of all, I would like to start with the very well known that first of all, last year we had again an all-time high in energy consumption. So no matter what we discuss and what we are aiming for, so the energy consumption is increasing. And I calculated whatever is in the field, and came to 30.5% renewables. The rest is fossil and nuclear. And yeah, we have to find ways to close the carbon leakage from the geosphere to the atmosphere. So that's what this is all about. And if we look into the future, we have three big areas why energy consumption will increase. First of all, the energy demand of emerging and developing countries, and whatever is not blue belongs to those. I was just in India 2 weeks ago, and they have like close to 7% GDP growth, which again transfers to a far increase of coal, and they are not shy in admitting that this will all based on coal, so at least for the next decade. Second, seawater desalination due to climate change. Of course, we have an increase of water, of sweet water in the various economies and regions, and this will be a tremendous increase also in additional energy. And third, as we discussed, negative emission technologies. Of course, we have the point sources, but we have to also take care of carbon out of the atmosphere. I think it's well known we have now 50% higher CO2 content as compared to 150 years ago, so 420 as compared to 280. So that's why we have this mess. And this is the only slide which you might memorize, because that's a German situation, the energy system for Germany, final energy, direct versus indirect electrification. On the left-hand side, you see, let me see if I can use this pointer somehow. Maybe not really, but yeah, it's obvious on the left-hand side. Yeah, I try my best. So here we go. Thank you so much. Yeah, so that's somewhere where we are today. So that's Germany, but this reflects also the world. So roughly about 20% is electrons. That's fossil, and down here we have the district heating and biofuels. And that covers a little bit the discussions we had today. We are not competing molecules and electrons. We have to close this gap. I mean, we have to get rid of all this gray part, and somewhere now here the discussions start. And of course, like if we listen to Robert Schlögl, so he would say, okay, let's just replace the fossil molecules by synthetic molecules, and let the rest somehow stay the same. But if we talk to Dirk-Uwe Sauer, who just left, he would say, okay, let's try to electrify as much as we can. And we are both right in a way. So as much as I would say it doesn't make sense to fly airplanes with a battery, as much Dirk-Uwe Sauer would say it doesn't make sense to have a passenger car based on hydrogen or e-fuels, since we have batteries. These are both statements of the same coin, but from different sides. But it's clear that at a certain point we will see a competition between direct and indirect electrification in various sectors. But it's very obvious that there are green hydrogen fuels are non-regret solution for industry and transports and at part of the transport sector. Yeah, but where this crossing line will be, I don't know. I only know that we need both at a certain point. And if we talk to the all-electric people, and they would say that the backbone of the future energy system is renewable energy, and there are good news, as you can see. We have 3.5 terawatt global renewable capacity, and solar is ramping up tremendously. And even better news is this one, that the power purchase agreements of PV is on the order of like 1 cent per kilowatt hour. And wind, I'm a physicist, I'm just interested in the order of magnitudes, but roughly like 2 cents per kilowatt hour is wind onshore. Offshore is like 3.5 to 4. So, but this is where we are, and this is still the early beginning of the hockey stick. We did, in the frame of a terawatt workshop over the last 10 years, we made this publications. What you see here is the cumulative installation in blue. We have about 1.2 terawatt PV installed right now. The annual increase is on the order of 300 gigawatt, which is wonderful. What we need over the next couple of years, let's say 10 years at the most, we need an increase of 10 times as much as we have right now, which means like 3 terawatt PV plus installation every year in order to reach roughly the 75 terawatt by the mid of the century. And this is needed if we are serious with our targets. If that's realistic and under which circumstances and which investment, this of course is a bit open, yeah, but increase by a factor of 10. On the other hand, this is the, I started this 3 years ago, but I have to stop this now. These are the strategy, the front pages of the national strategy papers of countries about, you know, their plans, how to reach net zero and how hydrogen will be included in that. That's all about gigaton and giga dollars and so on. So there's a big excitement. I would call it like a promise of salvation. So hydrogen should solve all issues which we are dealing with, you know, both as pure hydrogen or as derivatives. And how this looks like in a similar way, we have seen that with Robert's presentation this morning. You start, of course, that's always the same with whatever you have in terms of renewables, green electricity, and of course you would use it wherever you can, but electrons are limited to grids, and grids are not everywhere, and grids are not everywhere stable, even not in economies such as whatever South Africa as an example, which is the most developed country in sub-Saharan countries, and still they have hours per day of rolling blackouts and so on. So therefore, we need the option to transfer the electrons into hydrogen, and using the hydrogen wherever it can be used as an energy carrier in industry or transport, as we discussed. Yeah. The other way is using either carbon or nitrogen as a source. Carbon is, of course, available as a point source. Sometimes you get in issues with the credits when it comes from steel or from fossil sources. But nevertheless, I mean, with methanol synthesis and then longer chain molecules such as DME, OME, jet fuels, and so on. So this is the realm of the hydrocarbons as we have them now, but even better because the properties can be tailored and they can be even better hydrocarbon fuels in a way. And then I'm really glad that we had Markus Ohles and Carla Seidel today, because here this is exactly what we need. Also the defossilization of the chemical industry and of course fertilizer. This is the ammonia route, and ammonia offers of course the possibility to be a carrier of hydrogen. Let's look into all the overviews and so on, just to give a rough idea. There are on the order of 1,000 projects on the large scale of hydrogen production globally. This is the survey or the numbers of the hydrogen, what's it called again, the Hydrogen Council, which is comprises like 150 stakeholders globally. And if you add up the numbers, it would be 300 20 billions. This is even from last year, so the latest review is just coming out soon. But only 10% has seen the final investment decision. So it's also interesting to see a lot of talking, especially, I must say, Europe. That's the biggest. They have the biggest mouth, to speak. Yeah. Here it's too much talk, too little action. So, but nevertheless, what you see here in all these orange dots, that's all announcements by EU, but very little has been seen the FID. So that's has to be clear. But there are three major guiding structures. Of course, IRA, as we have heard, this can really be a game changer with these tax credit systems. In Europe, after the deep breathing came back, they tried to install the hydrogen bank, which is a somehow similar system. In Germany, we have the H2 Global program. It's stuffed with 3.5 billion euro now, and this is a double auction system. So the cheapest offer from the world is being connected with the uptaker who can pay the most. So this is one thing, and what just came out like 2 weeks ago is from the IEA, the Global Hydrogen Review. It's very similar in a way. So you see here all these big projects. By the way, this is a 20 gigawatt PV wind to hydrogen project. Hydrogen in Australia, this is really the big thing, so to speak. You know, they really, just in Western Australia, on the order of 100 gigawatt in total, are somehow in a phase of development and pre-FID phase. Yeah, it's also interesting that China, in 2020, it was like 10% of electrolyzer capacity. End of this year, it will be 50%, will be sitting just in China. So I would say in all silence, but again, it's like similar to PV. I mean, they are ramping up dramatically also to face their own needs. You know. This is an interesting chart which combines the suppliers and off-takers. On the left-hand side, since I talked about China, this will be by far the biggest market. They need a lot, but nevertheless, they are an even bigger off-taker. So this is what they need for their own defossilization needs from the various other regions and continents. The US is about equal. US will be able to export to other countries. Europe, you see here the 14, by the way, this is million tons per annum. This is expected in Europe, but the needs of Europe is like 4 times as much. So Europe will by far be an importer of large quantity. That's why Rotterdam, Port of Rotterdam, for example, Antwerp and Wilhelmshaven and all these ports are ramping up dramatically. It's also interesting to see, if you read all through these strategy papers, that regions not all think the same way. There is like kerosene is very much a South American topic at the moment. Africa the same. Green steel is related to Brazil and so on. So but ammonia definitely is an Australia thing, very much so. These are the expectations after the Repower EU last year, and of course there's a lot of fear of the future. So because of this new situation that we cannot rely on cheap natural gas forever. So therefore, it was just doubled overnight, the expectations, production and import 20 megatons in 6 years, basically, from now. So however that should happen. But the expectation, as you can see here on the right-hand side, by the mid of the century, it will be on the order of 2,000 terawatt hours hydrogen and hydrogen products. And the biggest market in green is certainly industry. Followed by power and heating plants. I mean, heating is probably also re-electrification systems and of course transport as well. So if you look into the countries in Europe, you again see that there is the big mouth, of course, as always, is Germany, the juggernaut in a way. That's our expectation. You see here, it's at least, I mean, this is still the lower threshold with 80 millions, but only like 20 or so can be done on our own soil, so to speak. The rest is import. Netherlands, which is number 2, there is about 1-to-1. So they will be able to produce whatever they would need, offshore mostly, and other countries, for example, like Spain can do the same, and the Dutch and the Swedish and so on, but other countries, they have very little ambitions up to now. Just a word about Fraunhofer, what we do. There are 36 institutes which have some activities in hydrogen, from very fundamental materials and whatever, quantum mechanical simulations of the diffusion rates of hydrogen in all kinds of materials. And on the other end, really the techno-economics of this whole system, and of course safety and life cycle analysis and so on. So there are roughly 1,000 heads which are somehow involved in hydrogen. And just to do a little bit of science, what we do at ESA, at my institute, the techno-economic studies, because it's very key at this phase. A lot of money has to be invested at the moment. As I said, 300 billion for the next couple of years. And investors, I mean, they're happy to invest in hydrogen, but they just don't want to lose their money for obvious reasons. So therefore, what's the regulatory framework and how much would be the cost of the various products? That's why we, together or for the H2 Global Foundation, we try to quantify all the costs at the sites, at the various sites. The regions were given by the H2 Global Foundation, and we used, of course, the obvious routes. So these are the dots. Oh, sorry, the reds should be in the green areas, but somehow that moved a little bit. Yeah, but these are at least the countries which are involved, and so we do that for like 10 years now, and I think we have a very good idea of how that works. We start with GIS analysis, local analysis for renewables and to power to X, with layers of like the landscape, if there's excluded areas, and or what's the terrain, what are the, of course, the wind and solar situations. So that's always a start. Now I know because that's not my computer, so that's why it's a little crooked, but you will get the idea finally. What's very important is the capital cost, the WACC factor, weighted average cost of capital. That's always decisive. And then we have hourly resolved the average meteorological data from the satellites for 1 year, and then we use the real world shipping routes to all these destinations. And then it's always it's a system optimization. It's always a question: is it grid connected? How is the water supply, desalination, and all that? So for each site, this is considered and modeled individually. And at the end, the output results is always like something like how much would the ton of a various product cost at this site, And there are, of course, Pareto fronts. That's not only one parameter, one thing. So it always depends a little bit on your basic requirements. What I also want to single out that this is, for example, it's Chile. You always have to transport electrons to the site. You have to have a carbon source. This is usually not exactly at the site. You have to transport that as well. So each site, these are just 5 of them, has to seen differently. So this, for example, is the tip of Colombia, that's La Guajira. It's a very windy peninsula, similar to the south of Chile and Patagonia. And Colombia is ramping up tremendously. They want to be the main exporter for Germany, which they are now for black coal, as an example. So, but each site has to be looked at very carefully. Texas was one of them, because it's if you zoom in exactly, so those sites. That depends very much on what you have to transport, how far is your way to a harbor, and all that, you know. But at the end, you get numbers like this. All the products which we looked at is hydrogen, liquid hydrogen, methanol, from two sources, the CO2 either from the air by direct air capture, because at the end of the day, so this is in decades, of course, this is the source to go. And second, if you have a point source and still get the credits. And it's very obvious that you need both solar and wind to have the high capacity factor, so that it's kind of a prerequisite to really be somehow competitive. Spain has very good boundary conditions, Northern Africa, the MENA regions as well, because they have also some windy places. So at the end, these are the columns which appear. So these are for 5 different areas: Chile, Texas, Australia, Spain, and what's that at the end? I forgot. But it's interesting to see, I think, that there is not one winner. So you see each column is a certain product. From ammonia, as I said, to the hydrocarbon products. That depends so much on the respective boundary conditions on site. And yes, and with this, I got the first conclusion. Yes, that there will be a peaceful, Dirk Uwe, just because we have a friendly discussions all the time between electrons and hydrogen derivatives. Yeah, it's a peaceful collaboration between both. So local electron use and production, as long as or wherever a stable grid and some storage is available, the rest is done by hydrogen per remote. And the circularity thing is getting key, because if you discuss gigatons, and I just came back from Japan where we started the so-called gigaton hydrogen workshop with the NREL and ICED. How do we get to gigaton numbers? The material cycles have to be closed, because if you look at this one, when we started with electrification, we just needed copper and iron, basically. And even with the first like cars or steam engines, it ramped up. And now just for the renewables on the right-hand side, we need not the whole periodic system, but we need so much. And therefore, it's so key that from the very first minute, we consider all kinds of circularity. And here that brings it a little bit into perspective, that especially rare earth elements and the PGMs, the platinum group metals, are key to consider from the very first minute, because they are rare and they're expensive, and we have to make sure that we don't lose them on the way. And finally, yeah, the point I made, because it's getting more and more clear that all these social aspects are, I'm a little scared about. Also the American situation, because my family comes also from the US and Berkeley and so on. So the coasts are okay, but all the mess with the house and with this loudspeaker called Donald Trump, so this can change so much. So we have to educate the people. So that's such a, and now we have the AfD, the right-wing party in Germany, also sitting in our necks for nothing, you know, they're not really helpful, but people are not, I mean, we pretend we're a rational people, we know what we do and we behave well, which we don't. We also fly around all the time, and but nevertheless, to keep the awareness of carbon high, so this is a very key action, so which is beyond our wonderful science as we do. And Finally, yes, we have to talk to our politics in terms of regulatory frameworks that they are set nicely. And the last word, of course, is about international research. The task is so complex and so big, so we can only work together and try to realize solutions. Thanks.
Thank you very much. So, if there are any pressing questions, please, we will take 3 maximum. Beatriz, please.
Only one very short one to let's say to Peidong, but also on the artificial photosynthesis, which is certainly still kind of a dream. But Peidong, what I found out or saw is that you are more going now in light-driven chemistry than in artificial photosynthesis. And the question is for me, could you just say what is a benchmark for your example with the pharmaceuticals?
Yeah, I guess you're asking about the benchmark in terms of production rates, right? Yeah, I think I mentioned this. Currently we're already at 10 milliamp per square centimeter for sort of this one sun irradiation on PN junction silicon. That's very decent because if you talk about solar to electron, that's only 20 to 30 milliamp, right? So if you can utilize almost half of those current and reduce CO2 into one particular C2 product with 100% selectivity, I think it will really make sense to think about a large-scale implementation. And then my last example of the red light-powered sort of device that makes this even more interesting because now you don't rely on the sort of day and night sunlight irradiation. You can run this 24/7 and you have a stacked device. So in terms of scaling up, it would be much sort of easier in this way.
Thank you. Dan Yakir has a question. Dan, please.
Yes, thank you. Yeah, that was a very interesting session. I have many questions, but I guess you are hungry. So one question about the artificial photosynthesis. Actually, it's also related to Uri's talk. In the artificial photosynthesis, I think you mentioned an efficiency of 4%. This is still in the order of magnitude of natural photosynthesis. And natural photosynthesis needs thousands and thousands of hectares of biomass production to make an impact. So the question I had is scalability is going to be a big issue unless you foresee a jump in efficiency from 4% to 40, 60%. Is this possible? And the related question is about heat management. And this was actually interesting in Uri's talk because he wants to expand the spectrum to use infrared radiation or near infrared, which introduce a major issue of managing heat production. But this is true in both systems.
Maybe I'll mention in our case of these hybrid photocatalyst nanoparticles, we are much more modest at this point. So a half reaction, the half reduction reaction in alkaline conditions, if you use it's been demonstrated for cadmium sulfide-based platinum system co-catalyst, for a half reaction, just reduction, you can get even 100% in a highly alkaline environment. But this is just a half reaction. So if we look at what we have in the photoelectrochemistry, which we just started together with Meni Shalom, the point was we are at 0.4 million. Peidong said 10 milliamps. This is now for a solar spectrum type of analysis. So there is a very long way to go. I know this, but we are at the fundamental steps in those kind of systems in our case, I have to say. Now, this concept of utilizing the other part of the spectrum, is still a principle that there is this concept of plasmonic photocatalysis around, promoted by various groups under illumination. And the idea that lies behind this is the combination, both plasmonic, but still use the other part of the spectrum for excitonic. In that case, if you will harvest these electrons so quickly, then you will not have heat, you will have chemical work. So that's the idea. So somehow to use those photons and not lose them for heat. Yeah, that's.
Yeah, I can quickly add, actually, in terms of the spice-free operation of these photochemical diode and the Wansan, energy conversion efficiency, in theory, it definitely cannot go above 40. I would say reasonably, we're talking about 15% solar to chemical energy storage. 15% would be, if we can get there, that's already a big milestone.
What I said about 100% is the quantum yield on a single wavelength, and that's different from the total solar that Peidong was mentioning, which is the relevant number for application, of course. But that depends on the spectrum and so on, integrated with this quantum yield effect.
Well, by the way, I mean, in natural photosynthesis, in terms of the quantum efficiency, basically once the photon goes in, the electron goes into reactive center, that's quantum efficiency is 100%. But in natural photosynthesis, energy conversion efficiency is 0.4%.
Yeah, but this quantum efficiency is not the practical one, and the 15% is still going to be a big challenge in scalability.
I agree. I think if we can get it to 10 to 15%, I think in terms of scaling up is something we need to follow the PV industry, silicon PV industry. Because at least in our device, we use like a 6-inch wafer now in that level. So when you think along that similar directions.
But you know, if you compare to natural systems, natural photosynthesis evaporates massive amounts of water to manage temperature. And if you will need to manage temperature like we manage our computers for climate modeling, this is another issue that is going to be a problem.
Yeah, I completely agree on that thermal management. This is not something we have been sort of focused on, but when we're getting to really steadily getting to 15%, we do need to worry about that thermal management, for sure, yeah.
I don't want to interrupt the discussion, but I'm doing it just for time reasons and for wrapping up. I think one key thing is that, and we had some conversation over lunch, is scalability, but also testing solutions under real life conditions with all the implications and trade-offs. I come from the climate science, and trade-offs are hugely important, you know, because if you go into geoengineering, that, you know, it's one example where you have to be very, very careful what happens in real life conditions. Just to wrap up, we had today some massive input of information. And I will not go through all the session, but I just want to say at the end, it seems to me as the organizer that there is a lot of need for discussion, and that's something that in some conferences it's completely different, and I'm very, very happy that this conference, this symposium is different. It's good that we have people from the industry, also yesterday, to see, you know, their point of view. It's good that we ask critical questions on emerging solutions, also on basic research, on modeling. I've found your presentation very interesting, also because of the price aspect, which concerns everyone here at the table. And it seems to me that, at least from today, some of the presentations, you know, after the presentation, the discussion, you had some questions that you didn't have before. And I think to take questions with you is very, very important.